This recording is for Physics 11, for the simulation that we did in class about energy skate park. This simulation is from University of Colorado, and it shows the distribution of kinetic, potential, thermal energies in the energy skate park. From 4 options, we chose the tab that's called Measure right here. And the goal is to have our object, which in my case is a 15-kilogram cat, slide up and down on this energy skate park on a skateboard, observe its motion, and observe the distribution of energies, do some calculations with the final idea to be able to know the speed of the object at any point in the track. So the key elements in this case are the knowledge of kinetic and potential energy. I'll hit a pause here. The object is currently in slow motion. I can hit normal and be going a little bit faster. But I'm going to pause this right here. I'm going to use the measuring tool, which allows at any point on the track to have the values for kinetic, potential, and total energy. Now, just a few notes about the setup. I have the speed currently ticked on, so it measures my speed. I have gravity set to be the Earth's gravity. There's a drop-down menu where you can select any planet. And I have an object of 15 kilograms, a cat, where you can change mass and you can change face and so on. And you can play around with it. In the highest point, which is currently 5.8 meters, I have measured that kinetic is 8 joules, potential 853 joules, total 861 joules, thermal is 0. That is because I have friction as none, and in all further labs, that is the setting that we want. We're not taking friction into the account. The total energy is the sum of all, thermal being always 0. My distribution will be between kinetic and potential energy. The key element is to know that at the highest point, kinetic energy is close to 0, and full total energy is potential energy, which is the energy due to the height 5.8 meters. There's a formula for that, which we studied in class, which I will show you how to calculate. And I can use this probe to test energy at the lowest point. The total energy should be the same as in the highest point. That is the key in the law of conservation of energy. There's no energy loss. 861.8 should be the same as 861.8 in the highest point, and in any point for that matter. You see this number for total does not change, and that is the case. That's how it should be, regardless of the object, regardless of the mass. This number will stay the same. The speed, however, is now increased. If in this case we had very small speed close to 0, this is the maximum speed, and that is because there's almost no potential energy, and the object have gained all kinetic energy and the maximum speed. It is also possible to calculate this number, which is the point of this simulation. And we should be able to calculate the speed at any other point on the track by knowing the height. This measuring tool allows me to measure the height at any point on the track, and I should be able to use calculations of total energy, kinetic, and potential to figure out the speed and confirm that the speed is in fact the same as the measuring tool shows. So this table shows the distribution of energy at the highest point, lowest point, and midpoint. My object is a 15-kilogram cat. My gravity is the Earth's gravity. This is the height in meters, the first column. The second column is potential energy in joules. Next is kinetic energy in joules. Next is total energy in joules. And the last column is velocity in meters per second. At the highest point, where we measured 5.8 meters, the potential energy is equal to, using the formula, mass times gravity times height, 15 kilograms cat times 9.8 the Earth's gravity times the height 5.8 is equal to 852.6 joules, which is very similar to the total energy I have. There's certain inconsistent, but 852 is very close to 861. Kinetic energy at the highest point is 0 because there's no velocity, and the total energy of the object is equal to 852.6 joules, exactly the number of the potential energy of joules. In the lowest point, this line, the height is 0. For that reason, potential energy is 0. mgh includes 0. There is no potential energy. Full energy that we had, E total, which is the same all across points, is now belonging to the kinetic energy. 852.6 joules is full kinetic energy. And now we can find the velocity. The formula for kinetic energy has mv squared divided by 2. So from there, v is the square root of this expression, 2e kinetic divided by mass. So 2 times 852 divided by 15 is equal to 10.66 units of measure meters per second, which is very close to this 10.71. This measuring tool helps me to confirm that my calculations are accurate. In the midpoint at 1.38, here at this point, there's a distribution of energies. I can't really say that one of them is 0 now. I can't say the energies are equal. That would not be true either. So I have to start by calculating potential energy because I know the height. So mass times gravity times height, 15 times 9.8 times my height, which is 1.38, will give me 202 joules, which is very close to what the measuring tool is here showing me. 202. Kinetic energy will be the difference between the total minus potential, 649.74. Quite close to my value. Total is still the same. This is the most interesting column that does not change. The energy does not disappear. It just converts from kinetic to potential across the track. And now I can calculate the speed, square root of 2e kinetic divided by mass. I just figured out that E kinetic is 649. So I put this into the formula here, divide by 15. I get about 9.3 meters per second, which is, according to the measuring tool, is exactly correct. Now, following the same pattern, I invite you to take any other midpoint somewhere. It's called midpoint, not because it's specifically in the middle, but kind of somewhere between the highest and the lowest points. So take one of the other points and calculate your own values for kinetic potential and speed, and confirm that that in fact is true using the measuring tool provided. So that is the nature of this simulation, is to be able to confirm your findings algebraically.